Welcome to The Explainer. Today we're diving into something that is literally the bedrock of modern technology. We're talking about computational loops. Have you ever looked at a super complex automated system and thought, how on earth does this thing not just break under the weight of doing the exact same thing over and over? Well, it all boils down to loop logic. We're going to explore how swapping out manual, tedious effort for computational efficiency actually works in practice, and how it lets systems scale up beautifully.
Okay, I want you to picture this. Imagine having to manually program a robot to clap to the beat of an entire 3-minute song. If you don't use the right logic, you're stuck hard-coding hundreds of individual commands. Clap, wait, clap, wait. Honestly, it sounds like pure torture, right? From a systems perspective, that kind of algorithmic overhead is completely unsustainable. I mean, why write the word clap 100 times when you can just say, hey, repeat this 100 times? Translating that basic, common-sense human intuition into scalable machine logic, well, that's exactly where our journey begins today.
Okay, let's dive into this. The contrast you're seeing here is just wild. On one side, you have this huge burden of manual, redundant commands. Every single action needs its own line. It bloats the code, it completely eats up processing resources, and honestly, it just leaves the door wide open for human error. But then, look at the other side. You have this incredibly clean, elegant alternative. Just repeat 10 times. That one simple, logical instruction gets you the exact same result, but it instantly cuts out all that useless redundancy. It literally transforms a fragile, bloated script into a lean, mean set of instructions that a computer can execute flawlessly.
So what do we actually call this elegant little solution? It is, of course, the programming loop. As you can see defined here, it's basically the ultimate method for achieving real computational efficiency. Instead of typing out redundant commands until your fingers hurt, a loop condenses all those repetitive actions into one simple logical instruction. Think of it like a massive force multiplier in software architecture. You define the rules just once, and the system handles the heavy lifting at scale. This is exactly what allows complex programs to chew through massive datasets and run continuous processes without needing an endless, unreadable scroll of code.
Now, let's look at how this abstract theory actually plays out in dynamic action. Our source material perfectly describes this continuous cycle as the never-ending dance. And honestly, that's a fantastic way to think about what a loop really feels like when it's running. It's this continuous rhythmic cycle just churning through data. But it begs the question, right? How exactly does the system keep that rhythm going? And maybe more importantly, how does it know when the dance is over so it doesn't just keep processing out into the infinite void?
Let's walk through this logic exactly the way a computer sees it. First up, we kick things off at start. The program executes the main action, which is clap hands. Then, bam, it hits a critical junction. This is a definitive decision point asking, is the song finished? If the answer is no, it loops right back around, repeats the action, and keeps the whole cycle alive. But if the answer is yes, it just stops. It is this perfectly contained, self-regulating ecosystem. It handles all that repetition completely seamlessly, without us needing to jump in and hold its hand every single step of the way.
Now, what's really interesting about this slide is that the absolute brain of this whole operation is that specific condition we just talked about. Without a condition, like asking, is the song finished, you accidentally create what's known as an infinite loop. And in the real world, that system would literally just keep running until it chewed up all its memory and crashed hard. The cycle is only allowed to continue until that specific condition is actually met. The exact millisecond that condition is satisfied, the loop breaks and the program moves on. It's just such a brilliant way to keep total control over a super fast, highly automated process.
And that brings us to the ultimate payoff here. Mastering this kind of logic empowers creators to write scripts that are just vastly more efficient. Like the quote says, the code becomes shorter and smarter. It's shorter because we completely ditch that bloated, manual redundancy that slows down both you and the computer's processor. And it's smarter because we're using those built-in decision-making conditions to route the logic on the fly. You basically stop being a typist, just hammering out boring one-by-one commands, and you become an architect. You're building intelligent, self-sustaining systems that do all the heavy lifting for you.
As we wrap up this explainer, let's bring this computational logic back down to earth and apply it to how we actually operate every single day. Think about your own routines for a second. Think about how you handle a mountain of emails, or how you organize a huge project. So what other repetitive actions in your daily life could be solved with a simple logical loop? Where are you acting like that bloated list of manual commands? And where could you apply this shorter and smarter logic to get your time and your mental bandwidth back? Once you start spotting these efficiency cycles, I promise you, you're going to start seeing opportunities to optimize absolutely everywhere.